All right, so let's take a look at upcoming schedule. The stuff in gray you won't see on your calendar quite yet. I think it'll show up probably tomorrow. But in any case, that's stuff that's after our test. And we'll be talking about some of it from the first assignment on Tuesday next week. So it's really very closely related to and just an extension of stuff we've already talked about. But upcoming a week from today is your test. We'll be taking the test using the Respondus Lockdown browser with the monitor, the webcam turns on when you start up the lockdown browser, and it just records you taking your test. So the test will be during regular class time. Have a little bit of extra time in case you have a problem getting started up, but it's an hour-long test and covers, well, we'll talk about the list of all the topics, but that's been posted on Canvas for a while. What I wanted to do first was take a look at some of the questions that were requested from the homework that's due next Tuesday. So the Friday homework is just strictly implicit differentiation. The Tuesday assignment is all the applications of that with related rates. So let's take a look at some of these questions. And let's see, from the first 5, the most requested was number 3. So this one says the length of a rectangle is increasing at a rate of 7 centimeters per second, the width increasing at a rate of 4 centimeters per second. When the length is 20, the width is 25, how fast is the area increasing? So let me start up my writing doodad. So just like with the, there we go. Just like with the optimization questions, look at the end to see what it's asking for. I want to know how fast the area of a rectangle is increasing. So these related rates problems, it's not asking for a maximum or a minimum, it's just asking for a rate, how fast. And it's how fast an area is increasing. So we're dealing with a rectangle. The only general formula about rectangles that we have is that the area is equal to the length times the width. Nothing about rates or speeds or anything like that. So if you know something, however, about how the underlying quantities are related, so this is what the previous keynote that we did in last class referred to as a quantities equation, how the length and the width form the area, then we can differentiate this to make rates from it, to make a new equation. So the area of a rectangle is given by taking the length times the width. And if I want to know something about how fast the area of a rectangle is increasing, now the how fast is described in centimeters per second in all the other things. So I've got the length increasing at 7 centimeters per second. So this is dl dt, the rate of change of the length with respect to time, just using the general t for time. And this is how fast the width is increasing, dw dt. Note that those aren't involved in this equation. What we're trying to figure out is how fast the area is changing, dA dt. So I can get all of those if I take a derivative with respect to time of both sides of this equation. So this relationship area equals length times width, if that's true, and these are changing, that'll make this change, and they must be changing at the same rate given by this equation, not meaning that they must be, it's not dw times dl, because guess what has to happen if you're finding the rate of change of a product? We need product rule. Now on the left-hand side, we don't. The derivative of a with respect to t is just literally called dA dt. But to find the derivative of a product, I take the derivative of the first times the second as it is, plus other way around. The derivative of the second times the original first factor. So our formula that relates the rates of change doesn't only have the rates of change, it also involves knowing the actual width and length. But this is our related rates equation. This tells you how changing one changes the other over time. So changing the length at a certain pace, centimeters per second, will have an effect on the area, whether or not I'm changing the width, but we have rates of change for both of those. So this relates the rates of change, and so it's called a related rates equation, whereas the first one is just underlying quantities, doesn't have any rates of change at all. So now that I have a related rates equation, I should be able to find dA dt. So this is our unknown, and the other pieces are given. So the length is changing at a constant rate of 7 centimeters per second. So that's increasing at the positive 7. The width is increasing at a rate of 4 centimeters per second. And notice we need 4 items to find this result over here. I need to know the actual width at the same point in time as this length, and that's the other 2 numbers, 20 for the length and 25 for the width. So just plugging into this formula and we get a result. So I'm not going to do the computations, but that's the general idea with this. Start with a quantities equation and differentiate it to make an equation that involves derivatives. This equation does not have any derivatives or any rates of change involved. It's just a couple of measurements multiplied together to get a different sort of measurement. So from the second set of 5 questions, let's see, the most requested was number 8. Number 8 is a jogger running around a circular track. Let x, y be the coordinates and assign the origin to be the center of the track. So just so we can talk about positions relative to the center, we then have, you want to imagine a circle. Here's the center, it's the origin. If you want to draw axes, we can draw axes. But circle has a radius of 50, and the jogger is at a position 30, 40 at some point in time. But in general, it's going to be x, y, traveling around the circle one way or the other. Notice that it doesn't actually say what direction she's traveling. That's okay, we can figure it out from the information that is given. So I'm not putting in 30, 40 right now because that's something that changes over the course of this. She's jogging around this. The things that aren't changing, the radius is 50 feet. So the length of this line that I drew, for instance, is 50. So is the distance from the center to the edge anywhere else that I want to draw it. But the positions are both changing, meaning she's going around this. So she's not always at the same spot, but at some point in time, she's at the spot 30, 40. And at that point in time, her x-coordinate, the position left to right, is changing at a rate of 11 feet per second. So thinking about how this all works together, sorry, I'm feeling my dogs are going to make noise in just a second. This x is changing at a rate of 11 feet per second. It doesn't say whether it's increasing or decreasing, but for it to be something negative, it would need to say is decreasing or have a negative sign. So that means the x-coordinate is increasing, meaning, well, she must be going around the circle this way. Now, this isn't necessarily a constant. It's not always that. Otherwise, she'd be running a really strange way. Have to go like, she couldn't continue increasing her x-coordinate by 11 feet per second. That wouldn't make any sense. But the y-coordinate then is going to be shrinking because, well, the relationship between x and y, whether you want to think of equation of a circle with radius 50, or maybe even just think about, we don't need angles, but the x-coordinate part is the horizontal section. The y-coordinate part is the vertical section of this triangle here with radius 50. And x and y, regardless of the position, they'd have negative signs in other quadrants, but x squared plus y squared equals 50 squared, just Pythagorean theorem stuff in this triangle, or this is also the equation of a circle with radius 50, centered at the origin in the xy plane. So if you want to just think about the triangle, that's fine. If you want to think about the whole circle and think about this equation, that's fine. But as x and y change, all the different points that would make this true fit in a circle together. That's the meaning of that relationship. So in any case, again, here's a quantities equation. It relates these distances. They're signed distances because we could have negatives. But what we need to find is how fast the y-coordinate is changing. Her x-coordinate's changing at this rate. This number is dx dt then. So dx dt is 11. We want to find dy dt, and all we have is an equation with x's and y's. So differentiate both sides, the derivative of x squared with respect to t, this is a slightly more complex setup than the previous equation. It involved product rule, but this involves chain rule. The derivative of y with respect to t is going to be very similar, y squared rather. The derivative of 50 squared with respect to t, well, it doesn't have any t's in it, and 50 is just a constant. This is not changing. X and y are changing, and they're implicit functions of time. Those are changing over time. I don't know exactly how, so I'll just refer to it as x and y. But some formula would relate what's going on with x, and the derivative of x squared then is 2x times, since it's a derivative with respect to t, times the derivative of the underlying function. So this is like f of x squared. So 2 times x to the first power times the derivative of whatever x is. This isn't a dx in the front, otherwise we'd be done with that part. It's a derivative with respect to t. So the two halves to this sum work exactly the same. X and y, when they're squared, their derivative with respect to some other variable is otherwise the same. So dy dt. So in any case then, once we're to this point, we have a value for dx dt, we have an x and a y, and our goal is to find dy dt. So that should be a simple algebra equation from there. Just sum, subtract, and divide once you sub in the numbers. So, all right, the third question, questions number 11 through 15, the most popular choice for what to talk about today is number 12. This one can be confusing for not just the math reasons, but also if you're not particularly familiar with baseball, it doesn't fully describe what all is going on here. But I'm guessing many of you are. But I'm going to draw this kind of from a home plate perspective. So baseball diamond is actually a square, meaning these are 90-degree angles despite my drawing here. At home plate, first base, second base, third base. So the batter starts at home base, bats from here, and then runs to the bases, in case that doesn't sound familiar. But each of these sides, this isn't changing, is 90 feet. This is actually a square. These are all right angles. And let's just take a look at the first question. So batter hits the ball and runs towards first base with a speed of 20 feet per second. So the batter starts here and is running this direction. After just a second or so, they'll be, up a little ways. So there's still got a ways to go to first base, and it's farther to second and third along the path. But this question asks, at what rate is his distance from second base changing when he's halfway to first base? It's not talking about his distance along the path, because that would just be this 20 feet per second. It's talking about straight line distance, meaning when he's at home plate, he's the farthest away from second base he's ever going to be. Once he starts running closer to first base, although he's not running directly towards second, his distance to second base is getting closer all the time, until eventually when he's at first base, he's 90 feet away. He started out at 90 times square root of 2 feet away. So in any case, let me just draw one triangle in here at a time. If I want to talk about, the situation talks about is when he's halfway to first base. I'm not going to draw it exactly halfway, just because that's too small. But let's say he's here. However far he is, this triangle has this side and that side, not the ones he's running along. We don't know how fast they're changing. This one's actually not changing. We've got a right triangle where we're not measuring the distance between first and second base. We're measuring the distance between the runner and first base, which that's shrinking. And then, well, first and second base is always 90 feet. That's not changing. But the distance between the runner and second base is changing. So let me call this X since I have it going horizontal, and I'll call this H for hypotenuse. So X and H are both changing. This side isn't changing. These 1 and 2 are just first and second bases for reference since I tilted the picture. Here's the runner. So I want to know at what rate his distance from second base is changing. His distance from second base is H. So dH dt is what we're looking for to answer the question. When he's halfway to first base, that's to give us a number to substitute into our formula. But again, the underlying relationship between not dH dt, but h, the thing whose rate we found here, and let's see, we've got a speed of 20 feet per second. That's how fast this side is shrinking. And notice it doesn't actually say anything that sounds negative, like decreasing or getting less or something, but he's running toward first base. So this distance would be changing. Dx dt, x being as in the picture, would be negative 20 feet per second. dH dt is what we're trying to find. And so we don't have a relationship between these that we know offhand, but we know how x and h are related along with 90 in this triangle. Now I could use an angle and stuff, but I don't know any angles in this either. Well, actually, I could probably figure one out if we're halfway between, but we need to have a general relationship, not one that's specific to one position. So x squared plus 90 squared equals h squared would fit this triangle. And then h and x are both changing. This isn't. So when we go to take a derivative, it's going to look, well, kind of like the circle equation we just dealt with, because that was really, also a right triangle. 2x times dx dt plus 0, the derivative of 90 squared, since it's not changing. 2h times dH dt is the derivative of the right-hand side with respect to t. dH dt is what we're trying to find. Ooh, and my pen just went off. There we go. This is what we're trying to find. So we need to fill in numbers for the other three symbols. So x, well, if we're halfway between home base and first base, that'd be at 45 feet from first base. Dx dt was this negative 20. And h, well, we didn't figure that out, but kind of like the question we did on Tuesday, h and x and 90 are in a triangle together. So if I know x, even though I didn't know h automatically, I can solve for it. All right, be the square root of, what is this, 45 squared plus 90 squared. This is also going to be a 45, 45, 90, or not 45, 45, 90, a 30, 60, 90 triangle or something, isn't it? No, it's not. Sorry. I was thinking of the wrong two sides. But in any case, I can solve for this. 45 squared plus 90 squared, take the square root, and I get h. So I actually kind of know h, but then I have to solve for dH dt anyway. And notice it'll come out negative. This side is negative. By the time I divide by this h value, which is positive, I'll get dH dt as something negative, which should make sense. The hypotenuse of this triangle is shrinking as we're getting closer and closer to first base. So it should make sense that it's changing when we're halfway there. It'll actually be shrinking all the way along. And the second part to this question involves a different triangle, because we'd be measuring, instead of distance from the runner to second base, we'd be measuring the runner to third base. So just set up a different triangle. But same general principles. Pythagorean theorem will help. And just keep in mind whether your distances are growing or shrinking. And notice if he's running this direction, you can maybe expect his distance from third base to be getting farther. All right, so let me pick a couple that I want to talk about. First of all, I see one right here, this conical water tank with a vertex down. Again, for purposes of tests and whatnot, things like geometry formulas other than areas of squares and rectangles will be given to you. You don't have to know formulas for volumes of cones and spheres and pyramids and everything under the sun. Those will be listed, but it helps if you've worked with them to remember some general facts about them. So I've got a water tank, and it tells me the dimensions of the whole tank. So this one, in mine, it has, the radius is 12 feet at the top, and the whole cone from center of the so it's facing this way, vertex down. So the center of this circular surface down to the tip of the cone, that's 26 feet. Now, let's talk about water flowing into the tank at 10 cubic feet per minute. And I want to know how fast the depth of the water is increasing. So this is the height of the entire cone. This is not the depth of the water until the tank is full. This is talking about when the water's 13 feet deep. So if the water's 13 feet deep, meaning half full top to bottom, it's not half of the volume of the cone. But I just wanted to point out that, well, I know this is 13. That was given. I also know this radius, and it might not be immediately apparent why, but if you think about the geometry of what I just drew there, this cone fits inside that cone. This is a cone of water, and this is a conical container. If I were to take a slice down the middle and look at the surface of it, I'd have the big, I should have drawn this in green, my big cone, which is 12 in radius, and 26 this way in height, and the water inside of it is 13 feet. I've got similar triangles. I can think about the whole triangle. I just filled in half of it here. But just to think about, since we're talking about radius here, like, oh, well, if I've got a large triangle, 26 top to bottom and 12 across, if I have suddenly a 13 that shares the exact same angle here, you can say, oh, well, that's cut in half. This is going to be cut in half also. You can solve for it with proportions if it's not such an easy thing as, oh, it's just cut in half. But it is actually this idea of similar triangles. And you can do the whole triangle all the way across along with the diameter. I just used this half triangle here since we were measuring radii. So just keep in mind, in terms of the volume of how fast the depth of the water is increasing when the water is 13 feet deep, we know actually also, in addition to the water being 13 feet deep, I also know the volume of the water then, because it has a radius at the top of that amount of water of 6 feet. So not going through this whole problem, but, I'll just point out while we're here. Volume of a cone, like other pointy shaped things, has a 1/3 in its volume formula. So 1/3 pi r squared times the height. So this can be the height and the radius of something that's forming a conical shape, like the water inside this, or it can also be the volume of the entire cone. But realize that the volume of this tank isn't changing. Nothing about the overall tank is changing. So just the measurements of the water are changing. But these are going to be in the same proportion at any point, whether it's halfway up, 90% of the way up, whatever. It's going to be this relationship between the height of the water and the radius of the water at that height, whether it's partially full or all the way full. That's going to be in the same proportion. All right, so one other thing I wanted to point out that has, let's see, some trigonometry involved. Let's see, where is it? I believe it's up in the first 5 questions. Maybe? Yep, kite. So a kite is 75 feet above the ground, moves horizontally at a speed of 4 feet per second. And we want to know at what rate the angle between the string and the horizontal is decreasing when 250 feet of string has been let out. So let me move this up a little bit. So just picture-wise, this is asking how fast an angle is changing. Since it involves an angle, we're not going to just use Pythagorean theorem, although that could still be helpful for us. We are going to have a right triangle that we can use as a part of this. Here's our ground. We've got a kite string. Let me just say I'm just going to pretend I tied it to a pole right here. There's a kite that's being held at 75 feet above the ground. So this is something that's fixed for this problem. Now, it's moving horizontally, which means, maybe it goes out farther. The kite is still 75 feet above the ground. In order for it to be out farther, there's a smaller angle and more string. The string goes along the diagonal. So let me just erase one of these triangles here. We'll just deal with one at a time. But you can see that as more string gets let out, the angle is going to be decreasing. But I have an angle relative to the ground that's changing. Let me call it theta, so I can call it something. This is not changing. This is fixed. And the length of the string is changing. The point that we're interested in is when it's 250 feet, but we'll use that 250 later. Now, the kite is moving horizontally. I could draw, instead of drawing the triangle this way, I could draw it like this way here. The reason I drew it this way is so that I can have an angle between the string and the ground, but I could draw it between the string and the horizontal someplace else. It'd just be the upper half of this, make a rectangle out of it and talk about this angle downward from the horizontal, which would be the same as this. So horizontally though, I'll just label it as X. The kite's moving horizontally, more string is being let out, and it's not going higher into the air, it's being somehow kept because of the way the wind's blowing at this height, and the string is just making it go out farther and farther this way. So X is growing, the amount of string is increasing, but this is staying constant. This theta here is decreasing, and we're asked about it. So although I could relate the length of the string and X and 75 with Pythagorean theorem, I can't relate this angle if I just use Pythagorean theorem. So the underlying quantities that I want to relate need to involve theta, so that when I take a derivative, I have a rate of change of this angle. So I can use whatever I want, but I have a rate for my horizontal speed. In my diagram, this would be dx dt, the rate of change of this thing I have labeled as x. And I need to find the rate of the angle, find d theta dt. So let me write an equation that involves x and theta somehow, and then we'll worry about plugging in numbers. So x and theta, well, x is adjacent to angle theta. 75 is not changing, so that would be a nice one to put in with it. Or I could say, let's see, that's opposite and adjacent. So let's go with tangent. Tangent of theta would be 75 over x, opposite over adjacent. I could move the x around, but then I'd end up with product rule. So here's a relationship between the angle and one of the sides of this triangle. And so I can talk about dx dt changing if I take a derivative, or x changing, values of dx dt. If I take a derivative, I'll get a place where I have d theta dt, because, again, we're taking derivatives with respect to time. So if I take a derivative with respect to t of tangent of something else, this angle is changing over time. Theta is a function of t, I just don't have it written out. This derivative of a tangent function, is secant squared function of the same angle, same input, and then chain rule. What's the derivative of theta with respect to t? d theta dt. And then on the other side of the equation, take a derivative with respect to t of, well, this is written as 75 over x. I'll call it 75 x to the negative 1. So I can just use power rule, not thinking about quotient rule here. So it'd be, what, negative 75 x to the negative 2, or over x squared if you want to plan ahead, times dx dt. So here's my quantities equation, relates some measurements in this setup. Here is a related rates equation. It relates the rate of change of x, horizontal distance, horizontal speed of the kite, the value of x, the value of, well, not theta, but of secant squared of theta, and I can find that without worrying about what theta is, and the thing that I'm actually looking for. So I'm going to use this space up here. So let me just get these labels out of the way. But if I want to solve this, I have numbers to plug in for everything but d theta dt, really. So secant squared of theta at this point. So a kite 75 feet above the ground. The moment that we're interested in, dx dt is 4, but that seems to be constant all the time. H is 250. Well, that'll allow us to solve for x, even though we don't have it. Let's think about, let's see, secant of theta, d theta dt, x squared, and dx dt. So we don't have x, but we can solve for it with Pythagorean theorem, right? X would be the square root of 250 squared minus 75 squared. So that's our number for x that we can put in that spot. Negative 75 times that number to the negative 2 power. So this in the denominator, squared. So no more square root, but it's still a huge weird number. Dx dt, well, this is our 4. X is increasing at a rate, this distance horizontally along the ground, making the string longer, is increasing at a rate of 4 feet per second. Secant squared of theta. So secant's the reciprocal of cosine. Cosine of theta would be x over 250. And I know what x is here. So secant would be 250 over x. So 250 over that. And then square it. So it's going to be 250 squared over that radicand, 250 squared minus 75 squared. So you can, it's messy algebra from here, but I don't have to find theta. Notice I can just find secant of theta as an expression without having found theta first, and then square the secant. And then since we have a number for this, a number for that, a number for that, it's just a matter of divide by this to figure out what d theta dt is. And it will end up being negative. This is a positive. This is a negative. Negative times something in a denominator squared. This is a positive. So we should end up with a negative value for d theta dt. As anticipated, because as the string gets longer, but this maintains the same height, that angle is going to be getting smaller. All right, so clear this off. And let's talk about, let's see, a week from today is your test. The test, there's a file on the Canvas page that says test 2 topics. So this was just updated in the fall. That's why it says something about fall 19 up there. But in any case, test 2, this picks up from where our last multiple choice test in class left off. So that went up through our accumulation sums, like how to estimate accumulation when given a rate function with the whole, oh, I really need to close this, with the whole sum of, oh, let's see, we have to count, use whatever you want, j equals 1 through x minus a over delta x, for count all of our intervals, and we had some r sub f of left, well, it was the left ends of all the interval values. So, but all this stuff, this was previous test, r sub f of a, and then r sub f of a plus 1 delta x, a plus 2 delta x, and all that, you know, this a plus j minus 1 delta x, all multiplied by delta x, and add on the one stray term for partial intervals. All of this, that was all last test. So after that, we pick up with how do I measure exact accumulation? And that's with an integral. So with integrals, we have our exact rate function. We measure it at every point, starting at a up through wherever we want, some x. But measuring at every point, we use it for just a little bit. So this is our m dx sort of expression. Sum them all up. That's the meaning of this integral symbol. And then we get our net accumulation, exact. So exact net accumulation starting at a and going through any value of x. We can find exact values by putting a number here inside those parentheses. But in any case, this is an exact net accumulation. So this plain old A versus A sub F, key distinction that is mentioned in this first one, and I'll let you read through the rest of this, we'll talk about it a little bit more on Tuesday, is that this is exact as opposed to approximate. We let t take on all of the values, all infinitely many of them, between a and x, and use each one for an infinitesimal amount of time, whatever this independent variable is, and add them all up, as opposed to having intervals of width delta x, which is like countable. There would be possibly infinitely many of them, but between any two numbers, you can say, oh, there's 17 intervals, there's 18 intervals plus part of one. I'm not ever going to say, oh, there's 18 different things to add up here. There's infinitely many, no matter how long this interval is when we're doing this exactly. But in any case, we can set up integrals. And then after that, so we went from an exact rate function to an approximate rate function, got an approximate net accumulation. And then to get exact net accumulation, we just shrunk down the size of those intervals, and this is the notation for it. This is what's called open form. It doesn't tell us how to compute this, and it's not a finite number of steps to follow, but it explains what has to be done. Open form indicates the process by which we get answers, even if we don't know how to do that succinctly. This is an infinite number of steps. So after that, we changed gears and we talked about, how do I get rate if I know accumulation to start with? If I know how much of something there is, how do I figure out at what rate it's changing? I should be able to do that. And this is when we started out just trying to reverse our process, but we found out that there are some catches in terms of being able to make continuous rate function graphs. We could get a whole bunch of little dots, but never connect them unless we came up with a new process. So if I have some accumulation function f, and I want to measure a rate of change in a moment around x, then I imagine a second spot that's h units later, and just imagine that h is very small, so that x plus h and x are extremely close together. And then, once I've written out an expression for rate of change in y over change in x, I'll have, well, change in y, take the y final minus y initial, divided by the change in x. X final minus x initial is going to be h, because that's how we set it up. And then imagine h to be essentially 0. Can't be equal to 0, but we did the algebra to work through how do I estimate this. And you can see what the pattern is if this expression can be simplified enough to be something basic, like maybe we can reduce out a factor of h, there isn't a denominator anymore. And so I can see terms that are getting closer and closer to 0 and just ignore them, saying, oh, well, that's getting closer and closer to 0. The rest of it that isn't is what the pattern is here. So that gives us our rate of change, not just for a single number, but a rate of change formula or function. So this open and closed form, we talked about that a little bit just now. Derivative rules, make sure you know them, but this test isn't focused on take the derivative of a function and that's the end of the story. We just took a mastery test a couple weeks ago, so this test isn't focused on that. You will need to be able to take derivatives in order to perform all of our applied problems, our optimization, our related rates, and also implicit differentiation, because that's a new type of differentiation that we talked about since the mastery exam. We also talked about logarithmic. That's not actually a part of this course, but you'll be using it a lot in Calc 2, so I wanted to give you a preview of that. But implicit differentiation involves all of the regular derivative rules and just some extra steps. Related rates is an application of this implicit differentiation, or seeing a symbol and knowing that it's representative of a whole function that we don't actually necessarily have to express on its own. How to find dy dx, or related rates problems, dA dt, whatever it might be. Let's see, so the first of these are in a slightly different order than what we did last semester. But let's see, coordinating accumulation of first and second derivatives. We did this kind of right after your mastery test. So looking at the graph of something, being told, all right, so this is a graph of an accumulation function. Tell me where its first derivative is positive. Tell me where its first derivative is increasing. There'd be numbers on here. Tell me where the second derivative is positive. Where might the second derivative be 0 or approximately 0? All those sorts of things. You had a lot of graphs like this in the homework. Or what if this is a rate function? Whereas if this is a rate function, whereas its associated accumulation function increasing or decreasing? Whereas this rate function's rate of change positive or negative or increasing or decreasing. And keep in mind the differences between positive, negative, increasing, and decreasing based on what it is that we're asking is increasing or decreasing, positive or negative. The function you see, the rate of the function you see, the accumulation of a rate function that you see. So in any case, think about those graphs and values of the first and second derivative along with patterns in accumulation if you're not given it. And optimization. So your last homework on optimization was due a couple days ago. You've seen a lot of examples of those. They're not easy. But again, most of the difficulty in those is setting up the objective function, the function whose maximum or minimum values you're trying to find, especially trying to figure out how do you write it as a function of one variable so that you can proceed and use our techniques of, well, where's the ends of the domain? Where are critical values within the domain? Places where the first derivative is 0 or undefined. But that is the content of your second test. Your second test is approximately 20 total answers to give. But like the first test, sometimes there's 2 and 3 questions about one diagram or one scenario that you have 2 or 3 different questions asked about it. So expect that on the test. There aren't 20 separate questions. I believe there's like 10 separate questions. Some have multiple pieces to them. But it is computerized and multiple choice. It's going to be just in Canvas using the Respondus lockdown browser with the webcam add-on. So try out the practice test. I'll talk about this again on Tuesday, but try out the practice test and see if you can understand how to use the proctoring system. You can do that practice on your own without my assistance. All right, so last thing I want to talk about, just kind of a visual recap of some of the stuff I was talking about this way. So let me just open up a Keynote. Let's see. I don't know why this is doing it this way. Open recent things. So we're going to be working some more on this next class, but this is a little bit of review between rate of change and accumulation. So just the typed up, neater than my writing version. So in the first half of the course, we worked on looking at how fast something's changing, and you want to know how much of it you have. So looking at a rate and generating accumulation from that. So suppose that the situation here is, if I have the rate function on the left there, an exact rate of change of my elevation, and I want to use that function r and its name to write an open form function f that gives the exact net change in elevation starting from a miles away from the border, or the coast, I guess I wrote border here and coast up above, up through x miles away from the same coast, let's call it. So there's this function over here. Just ignore this for a minute. We'll talk about that in a second. But if I have this rate function and I want to use that to write a function for an amount, a net change, starting at a and going through x, what we talked about was, and we just did this again a moment ago, if I know a rate and I want to know what happens because of it, I can get an exact value from this. The approximate we did before the first test. The exact we did right after. And we're going to be going back and forth for the remaining part of the semester. We're going to be going back and forth between finding rates and finding accumulations and using integral notation and getting out of integral notation. But if I integrate my rate function, this mdx expression, this rate times use it for a little bit of time. In this case, it's not really time, it's miles. So this rate of change in hundreds of feet per mile times a small, infinitesimally small number of miles, add up all the different values of that from A miles away from the border to X miles away, or the coast, whichever it is. That gives us this F, this exact net change function. So this is called, again, open form. It reflects the process. It doesn't tell us how to get something more useful, more usable, computable, but this accumulation is the sum of all the little pieces, each mdx, a rate times an incremental change in where I'm measuring that rate from. So I use each rate for a little bit of time, a little bit of independent variable value. So I'm adding up all these little bits until I get a sum altogether that ends at x. So suppose that E is an elevation function, not a net change in elevation, but just elevation. Notice that at 0, it starts at 300. So if this is actually a coast, then this is a cliff sort of coastline, as opposed to a beach coastline. So we start at 300 and it goes up from there. And I can see that, okay, these seem like they can go together. This is increasing rather rapidly at first, and then the rate at which elevation increases is still positive, but becomes lower. The slowest rate of elevation change, the slowest rate of increase is around 2.5 miles from the coast. And looking at this, I can see, yes, steepness-wise, this is fairly steep, but it's getting less steep. It reaches its least steepness right around here, and then it starts to get a little steeper again. So this seems like a reasonable graph to represent elevation with this rate of change of that elevation. So in any case, suppose that E is the elevation shown. F could also be written as E of x minus E of a. This expression here, y final minus y initial, gives me my net change in elevation between a starting point of A and any final x value. So E isn't the same as F, but I can express them related to one another. I can express either one in terms of this relationship here, this integral expression. This is a 3-part inequality, but I could put any two together that I wanted, and I could move stuff around the equal sign also. So I could say like E of x is equal to E of a plus this, or is equal to E of a plus f of x, which would be a weird thing to write. But these are all equivalent. They just express things in different ways. This is a function that has a longer definition. This is an open form process description of how this change in elevation happened. And this is a kind of final result. How did that, what was the change in elevation, final minus initial? So in any case, what we're going to get into next class then is some further explorations and review in this sort of area and what these integrals are, plus any other questions you have. So come with questions, or email them to me before class if you want, so that I get them, we can figure out what we want to talk about. Because next class is our last class prior to your test 2. And then after test 2, we just have 2 lectures, just kind of some summary information, and kind of putting all the pieces together, doing some slightly more advanced things with fundamental theorem of calculus, which we'll be reviewing next class also. But fundamental theorem of calculus tells us all of this sort of stuff. So that's next class. I will see you there.